I'm sure.
Okay, folks. Let's get started. So, my computer was acting up, so I'm hoping we're recording properly. We'll see. Before we get started, a couple of quick logistical items. Hopefully all of you saw my Canvas notification, but if you didn't, on the Canvas homepage, you'll find your group assignments for Lab 1, and they can remain your group assignments for all the subsequent labs if you so desire. I did my best to adhere to everyone's requests in that Google form. That said, there are 110 people in this class, so I have definitely made mistakes. So if you look at this and you feel like I've made a mistake with your group assignment as per your request on the Google form, just let me know and I'll fix it. It certainly wasn't intentional. As you get started in lab this week, another quick reminder. This is the first week where you're going to be writing your own code. So please remember that no code on the lab PC can be assumed to be there when you get back. Those PCs are periodically rebooted, and every time they're rebooted, all the user data is wiped. It's like a securities thing from CIT, which is just to say that when you finish working in lab, at the end of the lab section, make sure you either store your code on an external memory device, some sort of a flash drive, or some sort of cloud service. Email it to yourself. If you want to use Git, that's totally fine. Please just make sure that for your lab assignments, use a private repo. For your final projects, I'd encourage you to use a public repo, but for the lab assignments, please keep it private. Any questions for anyone? Okay, then what I want to do today is continue to introduce some topics that are going to be relevant to you for your week 1 checkout. In particular, I want to talk about Multicore, which is to say I want to talk about how we get code to run on that second processor that's contained in the RP2040. Remember from the overview diagram here, we walked through this a few times, but this is showing us all the hardware peripherals and all the stuff that's in the RP2040. And this is a dual-core microcontroller. There's 2 ARM Cortex M0s. If you were to just write some code with a function called main and run it, the default processor on which that code runs is processor 0. What I want to talk about today is how you get code to also run on processor 1. That's going to be relevant for you for lab 1 because you're asked to synthesize 2 crickets, one cricket out of processor 0, the other cricket out of processor 1. And then the other thing that I'm going to introduce today is Protothreads, which is the threading library that we're going to use to organize all of our code in this class. I'll talk about that in some more detail. But let me start with the multi-core stuff. And as usual, I'll talk through this with an example. And we will go, as we have been, to the Lab 1 incremental repository here. And at this point, we've talked through Blinky. We talked through the timer interrupt direct digital synthesis demo. This should look like an old friend at this point. We've covered every topic in here, except for fixed point, actually, which I'll cover in detail on Friday. But everything in here should look familiar. What I want to talk about today is multi-core direct digital synthesis. What this code does, let me talk about it for a second before I open it up. What this code does is it performs direct digital synthesis out of each core to each of the 2 channels of the DAC. Out of one channel of the DAC, it produces beeps of a certain frequency. I think it's 400 hertz. Out of the other channel of the DAC, it produces beeps of 800 or 400 hertz, whichever one is the other one. It's a little bit different than the previous example that we've looked at in that those beeps are modulated on and off, as you all saw in lab last week. But otherwise, it's about the same. So when we open this up, structurally, what we should expect to see is, if you remember our code from last week, when we looked at the timer direct digital synthesis code, structurally what we saw was some includes. We then declared some global variables and created some macros. We had an interrupt service routine. That's where the direct digital synthesis was occurring. And then we had a function called main, which was running on core 0. And what main did was, first of all, it set up all the hardware peripherals, and then it contained a while one loop that was just doing something, nothing important. So structurally, what we should expect to see when we open this up is, as before, we'll see some includes. There's going to be some additional ones because we're using Multicore. So we're going to pull in an SDK library that provides an API to the Multicore capabilities. So we're going to see some includes. As before, we're going to see some global variables and macros and such. What we should expect to see in this case is 2 interrupt service routines. One of those interrupt service routines is going to run on core 0. The other interrupt service routine is going to run on core 1. And similarly, we should expect to still find a function called main. That's going to be your code's entry point on core 0. We should expect to find another function that plays the role of main on core 1. It won't be called main, it's called something else, but it's your code's entry point on core 1. So that's what we expect to find is similar stuff to before, some includes, some global variable declarations, macros, etc. An ISR that's going to run on core 0, an ISR that's going to run on core 1, main for core 0, and main for core 1. So let's just take a look at this quickly. And what we see is, we'll first consider the includes. And you can see some familiar stuff here. In particular, we're including standard IO and math.h, just some standard C libraries. As before, we're including Pico standard lib, which I'll remind you, this does things like set up the default UART channel so that you can do things like call a printf. And if you open a serial connection to the board, you can read those things. We're now including another high-level library called Pico Multicore. We'll spend some time talking about that. And then we're including 2 lower-level hardware interface libraries, hardware sync and hardware SPI. Hardware SPI we've seen before. This provides an API to the SPI hardware peripheral. Hardware sync we'll talk about more today, but this gives you an API to those spin locks, which you can use to control access to resources that are shared between the cores. We'll talk about that today. Where do you expect to also see all of these includes reflected? In the CMake file. I'm reminding you because it's such an easy thing to forget. But let's just look quickly at the CMake file. You can see that we have our executable name, and then we are linking a few libraries here. This is our executable name. We're linking the standard lib high-level library, the multicore high-level library, and then these 2 hardware interface libraries. Okay, so those includes are also reflected in the CMake file. Okay, and then some familiar looking things. These are the macros that define our fixed point data type. We'll talk about this in detail on Friday, but that's all that's doing. Some macros and variable declarations here that should look nice and familiar to you now. This is all direct digital synthesis stuff. We then find our sign table declaration. We'll populate that in main. We find some variables where we will store the data that we're going to send to the DAC. And then we find some other stuff here. We'll see how this is used in just a moment, but we're going to use these things to modulate the amplitude of the sine wave on and off. So it ramps up smoothly to some max amplitude, sustains, and then ramps back down. And the names of these variables sort of suggest how we're going to use them. Attack inc is short for attack increment. That describes how much bigger the amplitude gets every step up to some threshold. And decay inc similarly describes how quickly it decays. And then we'll see how these are used in a moment as well. But these are describing for how long in units of interrupts is the amplitude going to ramp up, for how long is it going to sustain, and for how long is it going to decay. We'll revisit this in just a moment. Okay. And then some more familiar looking things. We're mapping, these are giving more readable names to the GPIO ports that we're going to map to our SPI channel. We're declaring 2 volatile ints here called core num0 and core num1. In these, we are going to store the value that we read from that CPU ID register that you may recall that I talked about that lives in the SIO. So this is one of those registers where if you're on core 0 and you read the CPU ID register, you get 0. If you're on core 1 and you read that register, you get a 1. So it's a mechanism by which your code can see which processor it's running on, which is a really nice thing to check. So among other things, what this example does is it reads the value of that CPU ID register in the interrupt service routine and prints it out just to confirm that the code is running on the processors that we want for it to run on. Okay, and then we find our first timer callback function, which is doing direct digital synthesis as usual. There's a bit more code here because it's implementing a really simple state machine that I'll talk through in detail today that describes how this sine wave should be ramped up, ramped off. There should be a gap, silence, and then it should be ramped up and off again. So this is the state machine. Again, I have a slide that sort of describes how this works, and we'll look at it in more detail. I'm just giving you a quick overview right now. But this is the state machine that you're going to modify slightly so that instead of going beep, 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 it produces sound and silence for the correct amount of time to simulate a cricket chirp. So you're going to augment the state machine a bit in lab this week. So this is one of the timer callback functions that's going to run on, if we believe the name here, core 1. Beneath it, there's going to be an almost identical timer callback function that's going to run on core 0. It is structurally exactly the same, just the names of the global variables are different. And then further down, we have a function called core 1 entry. This is going to play the role of main on core 1. Core 1 entry is your entry point to core 1. So your code on core 1 will start executing at the first line of this function. And we'll see how we set that up in just a moment. And then down here at the bottom, we find main, which is where I would actually like to start talking through this code in some detail. Okay. But all the stuff that we expect to find is there. 2 interrupt service routines, 1 on each core, a function that's going to be main on core 1, and then main, which is our entry point to core 0. And a lot of this stuff is things that you've seen before. In particular, lines 243 to 260 essentially is all at this point familiar. We're initializing standard I/O, printing a little greeting, initializing and formatting the SPI channel, remembering that the details of this formatting comes from the data sheet for the DAC, right? That's how we figured out, for example, what's the baud rate that we're going to set, what's going to be the bits per transfer, the clock polarity, the clock phase, and so on, all of the modes of an SPI channel. We get all those details from the data sheet for the DAC. We map all of the internal SPI signals to GPIO ports. Okay, and then we do some stuff that's a little bit new. In these 2 lines here, we are specifying, we are calculating the amount by which we are going to increase the amplitude of the sine wave when we're ramping it up per interrupt, and the amount by which we're going to decrease the amplitude of the sine wave when we're ramping down per interrupt. And we calculate this as a function of the attack time, the total amount of time that we want for that ramp up to occur, and the decay time, the total amount of time that we want for that, that amplitude to be attenuating. And these are all fixed point variables, so you can see that we're using that div fix macro, so that if we're dividing variables of type fix, then we're using this macro that we created in order to do that properly. Why is it important to ramp up and ramp down the amplitudes here of the audio?
Well, if you don't, you just have like a very it's almost like a square wave in terms of the audio, but otherwise you have a sine wave issue if you ramp up like that.
Yes. If we were to just turn the amplitude on full blast, so basically nothing's coming out of the DAC, and then we just start with a high amplitude sine wave, what we're sort of doing there is, what we're sending to the DAC is a sine wave modulated by a step function. And if you think about this in a Fourier sense, what is the frequency content of a step function? Think back to, what would this be, like a calc class probably? Whichever class where you were introduced to Fourier series. And probably one of the first exercises in that class was to come up with the Fourier series for a square function. And what you may recall is that with just a couple of terms, you end up with sort of a lumpy approximation to a square wave. You add more and more high frequency terms to that expansion, and you get a better and better approximation of that square wave input, which is just to say that a step function like that contains power at a whole bunch of different frequencies. Another way of putting this is if you were to look at the output of the DAC when you send it a square wave input with a sine wave in the middle. If you were to look at a real-time FFT of that, what you would see when the square wave comes is the whole FFT would go whoop, which is to say there'd be power at a whole bunch of different frequencies. What that sounds like to your ears is a click or a pop. It doesn't sound pleasant. It's an artifact. And your goal in lab 1 is to simulate a cricket. Crickets don't have that artifact, right? They smoothly ramp up the amplitude and smoothly ramp it back down. So that's why it's important for us to do the same. It's kind of interesting, incidentally, if you have time in lab and if you're interested in such things, turn off the smooth ramp and down and listen to it. You could even put the scope in FFT mode and look at the FFT of this thing. Or you could, I could show you how to do this. You can use the sound card of the PCs as a scope and generate a real-time spectrogram. And that's even more interesting, I would say, to look at, because when that step happens, you can see just noise at all the frequencies. So in any case, this is describing how quickly we're going to ramp up and ramp down the amplitude of those beeps. We're populating our sine table. The next thing that we're doing is calling a couple of C SDK functions that come from that hardware interface library called hardware sync. This is giving us access to those spin locks. Let me just pull up a picture quick. Just because perhaps it's been a little bit of time. So let me just remind you what I'm talking about. So in the data sheet, if we take a look at this section on the SIO, which is where?
2.
Right here. Thank you. Yeah. So this is what I'm talking about. You'll recall that that single cycle I/O block it contains a bunch of peripherals to which each processor needs low latency access. So, for example, it contains these CPU ID registers. Each processor can read that to learn which processor it is. It contains a FIFO for interprocessor communication, and then it contains these hardware spin locks, which I'll just remind you are a mechanism by which you can control access to something like maybe a global variable that both cores are trying to access. We'll see how this is used in a moment, but essentially, if I'm core 0 and I want to modify that shared resource, I grab a spin lock. And then when core 1 comes along and also wants to modify that resource, it will attempt to grab the spin lock. And if it's not available, if core 0 has already grabbed it, it will sit and block there until the spin lock becomes available, until it's released by the other core, at which point core 1 can grab it and do what it was going to do. So it's operating like a mutex. What happens if on exactly the same cycle, both core 0 and core 1 try to access the same spin lock? Ooh, did anybody read this? In that case, core 0 is preferred. Core 0 wins. So it is never the case that you will get a race condition on these spin locks. If it is the case that they're trying to access it exactly simultaneously, core 0 wins. Something similar is true, incidentally, for these GPIO registers. If both core 0 and core 1 on exactly the same cycle, suppose core 0 tries to set one of the GPIO registers and core 1 tries to clear one of the GPIO registers, your model for what happens in that case is, what it looks like to you is it's as if the core 0 instruction is executed and then immediately afterward the core 1 execution is executed in less than a cycle. In that case, what would happen is whatever GPIO or whatever core 1 said the GPIO should do is what you would see on the output. So if core 0 is trying to set it, core 1's trying to clear it, they do that on exactly the same cycle, the GPIO would stay cleared and you wouldn't see a blip up. Okay, so this is what I'm talking about here. So in line 274, we call a CSDK function called spinlock claim unused. If we wanted to, we could specify the number of a spinlock that we wanted to use. You may remember from a previous lecture that a subset of these, a pretty large subset actually, are reserved. The SDK itself is using some of these, and they're reserved for some other uses as well. So if you choose to grab your own, you just have to be a little bit careful about which one you're grabbing. This SDK function will grab one of them that's available. And if you cared to learn which one it actually grabbed, you could print out the value of spinlock num count, and it would tell you, oh, this is spinlock number 28, or something like that. And then we initialize it. So we call spinlock init for that particular spinlock. The next thing that we then do is call another CSDK function. This one comes from the high-level library from Multicore called Multicore launch core 1, which does exactly what it sounds like. This launches, it starts core 1, and as an argument, this function takes the name of the function that will be used as main on core 1, your entry point in core 1. So in this case, we're starting CPU 1 here, and we're saying start executing at the beginning of this function called core 1 entry, which is that one that we briefly looked at up here. And if you look in the SDK guide at the other functions that are available, the other parts of the API for this multi-core capability, you'll find options that allow for you to do things like specify a specific stack size for core 1 if you cared to. This is just using the default stack for core 1, which is after the stack for core 0. We sleep for a little bit. We set up the repeating timer. We talked about this last time. And then what's happening here in main, this is the code, of course, that's executing over and over and over again. All that's just setup stuff, right? Then this just runs over and over and over again. What this does is it grabs that spin lock, it increments some global variable, sleeping a little bit in between, and then it prints out a little message. It's printing out the value of that variable that's incrementing, and it's also printing out the value of this variable core num0, which we'll see in just a moment. In the ISR for this core, we're reading that CPU ID register to get the value of the core here. So this is just confirming that, okay, we are indeed running on core 0 in this case. So we increment a few times, print a few messages. We then release the spin lock, which allows for core 1 to do whatever it wants to do with that resource and do it all again. So that's what's happening on, so we've looked at main on core 0. The next things that I want to look at quickly are main on core 1, that core 1 entry point, and then I want to look at the 2 timer interrupts. So on core 1, when we call multicore launch core 1 and we pass the name of this function as the argument to that CSDK function, core 1 starts executing at the beginning of this function, just like core 0 starts executing at the beginning of main. And you can see that the first thing that we do here is we create an alarm pool on the 2 arguments for that alarm pool create function in line 210 are which of the low-level timer interrupts do we want to use for this alarm pool? Remember that there are 4 of them, so that argument could be 0, 1, 2, or 3. The default one, as it turns out, is number 3. So we are creating an alarm pool on a different low-level hardware timer. We're going to create an alarm pool on timer 2, low-level timer interrupt 2. And the 16 is just saying that we are going to allow for as many as 16 alarms to be in this alarm pool. The reason I'm doing this, incidentally, is remember that the 2 cores share 26 interrupts. Generally speaking, the interrupt service routine runs on whichever core configured and set up that particular interrupt. So on core 0, we are calling this add repeating timer CSDK function, this adds a timer to the default alarm pool, which is on low-level timer interrupt 3. So that means any alarm that's contained within the alarm pool associated with low-level timer interrupt 3 will run on core 0. So if we were to just call this function on core 1, we would add the repeating timer on core 1 to the, I feel like this is becoming convoluted. We'll go back through this again. But that would add the repeating timer that we're creating on core 1 to this alarm pool, the one that's on core 0. And if we were to measure, to access the CPU ID register in the associated timer interrupt, what we would realize is, oh, this interrupt's actually running on core 0, not core 1. So in order to make the interrupt run on core 1 as opposed to core 0, we have to configure the associated interrupt on core 1. So that's why we're setting up a different alarm pool on a different low-level interrupt on core 1, so that when we add a timer to that alarm pool, this associated interrupt and callback function will run on core 1 as opposed to core 0. That took me a long time to figure out. I could not figure out why the hell is the code not running on core 1. It turns out this is why. So in any case, we create this alarm pool on a different low-level timer interrupt, add a timer to that alarm pool, and then the main code that runs here over and over and over again looks really similar to the code that we just looked at. What this is doing is attempting to grab that spin lock. If core 0 is already has it, this is just going to sit and block here until core 0 releases it. When core 0 releases it, it'll get past this line and it will have obtained the spin lock. Then exactly like core 1, it increments that global counter and prints a little message, the value of that counter and the value of the CPU ID as read in the interrupts that we'll look at in just a moment. And then it releases the spin lock, waits for a millisecond, and goes back and tries to do it again. So what will happen in practice here is, once it releases this spin lock and sleeps for a millisecond, it'll come back up and try to execute this line, but in the meantime, core 0 will have been waiting on its associated line to grab this spin lock. So it'll sit and block here until core 0 goes through and does everything it was going to do. Okay. Okay, so the next thing I want to look at is these timer callback functions. You'll remember that last time when we were looking at the direct digital synthesis example, that callback function just contained essentially like 3 lines. It was increment the phase accumulator, look up the sine amplitude associated with that phase angle, and do a transmission to the DAC, and that was it. This is just slightly more complicated. The first 2 lines here, so there's 2 states. The state can be either 0 or 1, as we'll see in a moment. If we're in state 0, which is the state that we start in, we increment the phase accumulator, we do our sine table lookup. The slight difference in this case is that we aren't sending just the amplitude that we look up from the sine table. What we're sending instead is the amplitude that we look up in the sine table multiplied by this variable called current amplitude, which is just going to be some number between 0 and 1, so that we can ramp up the amplitude, sustain it, and ramp it back down. So we're controlling that ramp up, sustain, and ramp down by playing with the value of that current amplitude variable that we multiply by the sine amplitudes. So okay, we do our DDS stuff. We then take a look at the value of an incrementing variable, which in this particular ISR I've called count1. Every time we enter the ISR, we're incrementing this. And we say, okay, if we have been in state 0 here for less than the attack time, which is to say less than the amount of time for which we want the amplitude to be ramping up, then we increase the value of that current amplitude variable by the attack increment. We make it a little bit bigger amplitude. Likewise, if we have been in this state for longer than the attack time plus the sustain time, then we start to attenuate the amplitude. We subtract off the decay increment from the current amplitude. And in the middle, it's just staying the same. So this has the effect of ramping up the amplitude of the sine wave for the total attack time, sustaining it for the sustain time, and decaying it for the decay time. That we're doing that by controlling the value of this current amplitude. And then we do some very similar looking stuff. We mask in the DAC control bits, we write that data to the DAC, increment that counter, and then we check the value of that incrementing variable to see how long we've been in this state. And if we've been in that state for some threshold amount of time, which I'll justify in just a second, then we do a state transition. And in the other state, all that we're doing here is incrementing that counter a little bit. And when we have reached the threshold amount of time associated with the amount of time for which we want there to be silence, then we transition back to the other state. And I'm going to show you a graphic of this state machine in just a second to hopefully further clarify things. But that's all that's happening here. The consequence of this is going to be this will produce beep, pause, beep, pause, beep, pause. And the length of that beep and the length of that pause are controlled by this beep duration parameter and this beep repeat interval parameter. I want to just make a point about these very briefly. If we look at the value of these, you will see that the beep repeat interval, this is the amount of time for we want there to be silence, is set to 40,000. So what that means is a state transition will occur from silence to starting to produce a beep again when that counting variable, which we increment every time we enter the interrupt service routine, reaches 40,000. That timer interrupt is set up to run at 40 kilohertz. So how long will there be silence? 1 second, right? So the unit, the point that I'm making here is the unit of time when we're setting all of these parameters, the unit of time associated with how long we're ramping up the sound, the unit of time associated with how long we're sustaining the sound, how long we're ramping down the sound, and for how long we're pausing between the beeps. The unit of time there is interrupts. How many times have we entered the interrupt service routine? So there's a little bit of unit conversion here that you need to think about. You'll need to convert from the lab 1 write-up, gives you all the specifications for the timing of the chirp sequence in milliseconds. So you'll have to convert from milliseconds to interrupts, which is not so bad. It's just something to be a little bit cautious about. Okay, so let me just show you the state machine that we were just looking at in a slightly different way. So as I mentioned, we initialize the state to be in state 0. In that state, the following things happen. We increment the phase accumulator, and we scale the sine wave amplitude that we get out of the sine table by that amplitude modulator. We just looked at that in code. We then update the value of that amplitude modulator. Are we less than the attack time? We make it a little bigger. Are we greater than attack plus sustain? Then we make it a little smaller. We're starting to ramp it down. Otherwise, it stays the same. And we increment the value of this counting variable, which we're using to keep track of how long have we been in this state? How long have we been making a beep sound? The check that we then do when we get to the bottom of this state is we ask, has this variable reached some threshold value which we're calling beep duration, the amount of time for which we want the beep to be occurring? If the answer to that question is no, then we stay in this state and we do it again. We continue to produce sound. If the answer to this question is yes, we transition to the other state, and in that state transition, we zero the counting variable because we're using this variable to keep track of how long have I been in a state, a particular state. So every time a transition occurs, we zero it. In this other state, all that we do every time we enter the interrupt is increment that counter. And then every time we ask, okay, has this counter achieved this different threshold value, beep repeat interval, which as we just looked, what we just saw is that's set to 40,000, which is the amount of interrupts it takes to consume 1 second. If the answer to this question is no, we just stay in this state. We keep incrementing until we've been here long enough to transition. If the answer to this question is yes, we zero that counting variable, and we go back to state 0 and make another beep. So in lab 1, in lab this week, you are going to be augmenting this a little bit. your state machine is going to be composed of 3 states. You can call them whatever you want, but you might call it something like chirp. This is the state where you're actually making sound. Maybe syllable pause, which is the amount of time between each little chirp that composes a full, each syllable that composes a full cricket chirp. And chirp pause, which is the amount of time between each chunk of syllables. So you're going to have 3 states here instead of 2 states. And then you'll need to be counting the amount of time that you're in each state, and you'll also you'll need to maintain knowledge of when you're in, of how many syllables you have produced. How many times have I made a little syllable sound? The reason you have to keep track of this is 2 of these states, the syllable pause state and the chirp pause state, these are both the states associated with silence. These are the little gaps in sound. Both of those always transition to the chirp state where you're making sound. However, when you're in the chirp state, you've just finished making a sound, you have to do, it may be the case that you transition to a brief pause between syllables, or it may be the case that you transition to a longer pause between chirps. And in order to know which state to transition to, you have to be maintaining knowledge of how many syllables you've produced so far this chirp, right? So in each of these state transitions, you're going to zero that variable that you're using to keep track of how much time you've been in that particular state. And in one of these state transitions, you are also going to zero a variable where you're counting the amount of syllables that you've produced so far in that chirp. So it's a slight augmentation, right? Okay. The next thing I want to talk about, in 15 minutes, that's okay, is Protothreads. Protothreads, as I've mentioned a few times, it's the threading library that we're going to be using to organize our code in this class. And the tagline is, it's a lightweight stackless threading library. It was created by a guy named Adam Dunkels. There's a website associated with it. You can go read about how this actually works, and you should go read about how it works. But this statement requires a little bit of unpacking. So let me just briefly tell you something that you probably already know, but that's okay. But what is the threading library? If you first consider a, quote, I don't know what word to use, a normal microcontroller program, a microcontroller program that isn't using any kind of threading environment, the structure that you probably will find in that program is something like what we've been seeing in this class so far, which is to say there's going to be some includes at the top. You're then probably going to find some global variable declarations, maybe some macros created. You're then probably going to find a collection of interrupt service routines, one or a handful of them associated with various interrupts. You might find some helper functions declared, some other functions that are going to be used in the code that gets run over and over again. And then you'll find some function called main. And main is going to include a bunch of code that runs once, that does things like set up the hardware peripherals. And then probably, in a lot of applications, main is going to include some while one loop. And the code within that while one loop, as you all know, just runs over and over and over and over again, occasionally getting interrupted by an interrupt service routine. This code up here runs in the ISR, and then we come back to main, right? For those of you that have a lot of experience with like Arduino, this is sort of the structure that those sorts of programs often use. In a threaded program, it's similar in a lot of ways and different in some important ones. You'll generally find a slightly different structure. As before, you'll find some includes. You'll probably find global variable declarations and stuff. You'll find some interrupt service routines and maybe some helpers. And then what you'll find is a bunch of threads. And each of these threads looks, as we'll see, they kind of look a lot like a function. Except what's different about them is that each of those threads contains its own while one loop. It contains its own set of code that gets run over and over and over and over and over again. And the scheduler associated with this threading library will move the execution pointer from one of those while one loops to another one. So it bounces from this thread to this thread to this thread when you tell it to. So in main, then, what you see is very similar to before. You have a bunch of code that runs once. That code does things like set up the hardware peripherals. It also does things like add each of the above threads to the scheduler. And then it'll start the scheduler. And what the scheduler is going to do is context switch among all these threads. So why is this useful? Because as I've just explained it, you might think like, that sounds like you're adding complications, just annoying. But it actually, it's really useful. Suppose that you're trying to write some complicated program, like you are in this class for every one of the labs, and suppose that in that program, there are sections of code that you only want to run under certain sets of conditions, right? So for instance, when the big, dumb, slow human enters a parameter finally, there's maybe a snippet of code that you want to run that sets a parameter value equal to whatever that user entered. But you certainly don't want for your code to sit and block and wait for the user to enter something until that condition occurs. You want for other things to be happening simultaneously, maybe some animation to be running or something like that. Which is just to say, another way of describing what I'm talking about is you're writing some sort of a concurrent program where you want things to be happening simultaneously. They aren't actually happening simultaneously, but you want for snippets of code to run conditionally. You could accomplish this with a big state machine, no threading library, just a big state machine. The problem with that is once the applications get sufficiently complicated, that can get really cumbersome. You have to think really carefully about all the state transitions. And if you want to add some new piece of code to that state machine, it can be tricky to integrate it. A threading library makes this so much easier. So much easier, which is why we're using it in this class. The alternative to this is whatever that set of conditional code is that you want to run under only certain circumstances, you consolidate all of that into a thread, and you make the conditions under which that thread gets executed, gets scheduled by the scheduler, associated with the conditions under which you want that code to run. So maybe there's some code that you only want to run when some variable has assumed a certain value. Maybe it's a variable that's counting time, right? So there's some code that you only want to run once a second. Then you make you consolidate all that code in a thread, as we'll see in just a second. Make the conditions under which that thread is allowed to execute. The timer value equals some number, right? And then that code will only ever run when those conditions are met. So it makes the code really modular. So for applications like this, you benefit quite a lot from using a threading library. So this is true of threading libraries in general. Some of the properties of Protothreads in particular are it's non-preemptive. What that means is no thread will interrupt another thread. So if a certain thread is running, it is controlling the CPU. It will continue to retain control of the CPU until it yields. And you have to tell it when to yield. If you look at the API on the course website, there are a series of conditions under which you can have a thread yield. But it's up to you to yield control of the CPU from one thread to the other threads. It's stackless, which is to say there is no stack associated with each thread. So when a thread yields, any local variables contained within that thread are gone. So if you have local variables in any thread, as we'll see, you must tag them as static. This is another one of those keywords like volatile. You'll remember that a variable declared as volatile, its value will be looked up from memory every time it's used. A statically declared variable in a thread will have local scope. It will be scoped just to that thread, which is what you want, but it's stored as a global variable. So when you come back to that thread, it will have retained its value. And later on in the semester, I think we'll do a fun deep dive discussion about Protothreads. I'm going to save that. These work by utilizing a bizarre thing in C called Duff's device, which you should all go read about because it's interesting. We'll talk about it later in this class. Discovered by a guy, his last name's Duff. I think his first name's Tom. I can't remember. I think it's Tom. He discovered this when he was working at Lucasfilms. He was working at some optimizations at Lucasfilms. In short, what this is he noticed that a switch case in C could jump into a while one loop. So this is the mechanism by which Protothreads can jump from within one while one loop in one thread into another while one loop in another thread. Really clever, really, really clever. Okay, so let's just take a look at some code quickly. And the code that I want to look at is your starting point code for this week, audio beep synthesis. This is the code that you all got built and programmed onto the device last week. And a lot of this is exactly identical to the multicore code that we just looked at. So I just want to highlight the differences. In particular, let's scroll down to main here. You can see that the whole top part of main is exactly the same. The only things that are different here is we are calling a macro called pt semsafe init, and we're pointing it to something called core 0 go and core 1 go. These are two semaphores that we've declared further up above. So we're initializing two semaphores, one with a value of 1 and the other with a value of 0. And then the other thing that we're doing is calling a function called pt add thread. This adds a thread to the scheduler. We'll look at that thread in just a second. And then we call pt schedule start, and that just starts scheduling the threads. And if we look at the code on core 1, it's doing something very similar. Exactly the same as before, creating that alarm pool, putting a repeating timer in that alarm pool, adding a thread to the scheduler, ProtoThread core 1 in this case, and then starting it. Each of these threads looks like the following. We create a thread by calling a macro called PTThread. As an argument, this macro takes the name of the function which will instantiate this thread. We could call it anything we want. In this case, we're calling it ProtoThread core 0. And the argument that this function takes is a little bit of C gibberish, but this is a pointer to an object of type PT, which is defined in the ProtoThread header file. But in any case, this is how we create a thread. And then this is the whole thread. We start it with a PT begin, and we end it with a PT end. Every one of your threads will start with a call to the macro called PT begin and the macro called PT end. And then everything in the middle looks a lot like normal C, because it's mostly just normal C. What this particular thread does is it waits on a semaphore. So it will yield here until this semaphore is signaled. Once this semaphore is signaled, the rest of this code is allowed to run. This code, incidentally, is pretty much identical to the code in the other example that we were just looking at. In particular, it's incrementing a global counter and then printing out some values. In this case, we're not using the spinlocks because the other thread that's running on core 1 will only run when signaled by this thread. So these two will not attempt to access this resource simultaneously. And we're initializing one of these semaphores as 1 and the other as 0, which means that when the scheduler starts, only one of the threads will be able to run. In particular, I think it's the one on core 0. So the first time it runs, it'll pass this line, run, signal the other thread, and then wait to be signaled to run again. And if you look on the course website, let's just take a look here at, there's a page here on ProtoThreads that includes the API. So it describes how you initialize ProtoThreads. It describes how you create a thread. The various mechanisms by which you can yield a thread. You can call a PT yield, which means that the thread will yield, but then it's ready to go again as soon as the scheduler gets back to it. You can yield it until some condition is met. And there's some other ones that have been added too, incidentally. You can yield for a certain amount of microseconds. You can yield for a certain interval somewhere in here.
The third one down.
Third one down, thank you. So in any case, this is describing how you can control which threads yield when and which threads are allowed to run when. But it's up to you for this particular threading environment to do that control yourself. This was a fast introduction. I recognize that. A little faster than I would have preferred, but that's okay. On Friday, we're going to spend a lot more time revisiting this threading environment and going through some more examples and talking through a few more of its bells and whistles.